Hello everyone, very good evening. Welcome once again to today's class. We are starting a bit late, but we will be able to cover everything that is left in stacks. Okay. Uh, so stacks is one topic which does not have a lot of variety, I would say. If you solve some 8, 10, 15 standard problems, basically mostly in the class itself, we are doing all the standard problems. So, given any new problem related to stack, you should be able to do it, right? Infix to postfix, Chandra says. So it's a special algorithm, I would say. You don't need to really know that algorithm, right? But if if the problem is there in the assignment, I can take help from the internet, learn more about it, and do it. Okay. Otherwise, personally, from my experience, it's not a very important topic. um, so it's completely optional. You if you want to do it, you can do it. Okay. Infix to postfix problem, right? So pretty much a famous algorithm, so you don't need to apply your head to build it. You can take help from internet as well. Okay. All right. Let me just see what problems we did in the last class. Okay. So this is, I think um, we started with LRU, and what was the other problem we did? For every element, find the nearest smaller number, right? Yeah. So this is an important problem because today's class is also going to be using this problem, right? Stockspan also we did. That's correct. So the main problem that we solved in the last class was given an array of size n, find the nearest smaller number for every element that is present in there. Right. So I'll just copy this for today's class as well, right? And for that we built one algorithm. Right? So does everyone remember this problem? We solved such a question, right? Okay. So I'll just continue from where we left, right? So in previous class, what we learned is that for every element we can find the smaller element to the left for every array element, right? So we said this can be done in how much time? Order n time, right? So we built an order n algorithm using stack. This is what we have already seen, right? Now tell me, if I change the question, can you also find the bigger element on the left using the same algorithm? Tell me. Can I say I can find the next bigger element on the left using the same algorithm? Come on, yes or no? For example, if I talk about 4, the bigger element on the left is 6. If I talk about 12, the bigger element does not exist. It's minus 1. Right? Can I also say I can find the bigger element on the right? What will change in the problem? For this array, for let's say 4, I want to find out what is the bigger element on the right. So on just right, it is 12, right? For 3, it is 8. For 12, the bigger element does not exist. That's correct. So you have to iterate from um, n minus 1 to 0. That's correct. Right? And similarly, you can also find the smaller element on the right. Smaller element on the right. So all these problems, they can be solved using the same algorithm in order of n time by just changing the loop and the comparison condition, right? That is what you need to change, right? If you change the loop direction and the comparison condition, you can find all these elements in order of n, right? Great. So the very first problem that we will do today is a very famous classical problem, right? Now, Shubham, it will work for negative elements as well, because between big and small, it's a comparison. You will still say that, okay, -3 is less than 8, right? The comparison does not change, right? So it will work for negative elements as well. What may change is, you might not say -1, you might say, okay, I will put int min, or I will put something which is not a part of input, right? All right, that's correct. Okay, so we'll solve one classical problem which is actually based upon this idea, right? It is called as area of histogram, largest area under histogram. Maybe you might have heard about this problem, maybe not, right? Largest area under histogram, right? Does anyone know what is a histogram? Does anyone know what is a histogram? It's kind of a bar graph. That's correct. Ankur, you're right. Graph with bars. Absolutely correct, right? So, example of, so it is basically used in, it's a graph to represent data. It's just like a bar graph. For example, I'll just giving you one example, right? Maybe uh, I'm denoting the count of students who scored marks in a particular range. For example, where we are just starting off, we are telling you what is a histogram, right? So then we are going to solve a problem on histogram. Okay, so maybe I'm denoting the count of students who scored a particular marks, right? Maybe marks are a range, maybe between 50 to 60. Let's say there are out of 50 students in the class, 8 students got marks in this range, 50 to 60, basically 50 to 59. Maybe there are 3 students who got marks in this range, 60 to 70. Maybe there are 12 students who got marks in the range, 70 to 80. Maybe there are 5 students who got marks in this range, right? Maybe there are 2 students who got marks in the range, 90 to 100. Okay, so similarly, we might have certain ranges. Okay, now if you look at this chart, right, what is this kind of graph? This is called as a histogram, right? So what is actually storing? I'm storing frequency on the y-axis, basically number of students, right? The count of students, and on the x-axis I have a marks range, right? So each of these is called as a bar, right? So each of this is a bar, and it has a certain height. The height simply denotes the number of students. Okay, so it's kind of more used in data visualization, right? So the actual plotting, when you do machine learning and stuff, people do plot these kinds of graphs. Okay, so it's used in data visualization. Okay, but right now we are not going to do any kind of data visualization here, but what we are going to solve is a more like a algorithmic problem. Okay, so what is given to us? We are given an array that represents the histogram. Basically, we are given this array that contains these numbers, right? And we can assume that each bar is of 1 unit length, right? So let me show you one example. Let's solve this challenge, largest area under histogram. So let me first draw a chart, right? Let's say I have 1, 2, 3, 4, and 5, right? And I have an array like 1, 2, 3, 4, 5, 6, right? So I have 6 bars the first bar is of length height 2. Okay, the second bar is of height 4. The third bar is of height 3. The fourth bar is of height again 4. The fifth bar is of height 5. The sixth bar is of height 1. So this is given to me, right? And what I want to find is the largest area under histogram, largest rectangular area, right? Now, what does it really mean? It simply means that I want to find out the area under largest rectangular block that does not that lies inside histogram bars. Okay. Now, suppose if I start from this first bar, I say, okay, I will make this uh, as a part of the rectangular block, right? So, can I have this rectangle? Tell me, can I have this rectangle? No, because it goes outside the boundary of first bar, right? So, the maximum I can take is up to this much height, and maybe in this direction I can go this much. What do you think? What is the area in this case? Each bar is of unit length. So horizontally, I have a base, right? I have a base which is 5, and I have a height which is 2. So I'm getting 10 units. Fine. Maybe I consider another bar. There can be many bars, right? So maybe I might have this as the bar. Right? How much is the area in this case? The pink one. It has less width, right? So it has a height of 3 and base of 1, 2, 3, 4. Oh, in this case, it is 12 unit, right? Okay, maybe I can have some other area. Maybe I can say, let me take this. Right? So in this case, the green bar is of height 4. This is 2. This is 8, right? So there can be many such rectangles. Do you see? There can be many such rectangles, right? So what we are getting is we want to know the maximum area. So it seems the maximum might be 12. Like out of the rectangles that we have seen, the maximum it seems it's going to be 12, right? So this is what we need to find out. Okay. Tell me, are you understanding the question? Can we sort? No, no, you cannot do the sorting because that will change the ordering, right? So that does not make sense here. So sorting is not allowed, right? Under histogram. Okay, so histogram means you cannot change the order of the bars, right? So no reordering is allowed. Okay, please write the array. Yes, so array is like this. It is of height 2, it is of height 4, then it is of height 3, then it is of height 4, it is of height 5, and then it is of height 1, right? So it's a 2D array? No, it's not a 2D array. You are given a 1D array. So these are the bars, right? So this is bar 1, bar 2, bar 3, bar 4, bar 5, bar 6. These are the bars given to you, right? So the input is this array. The input is this array, and the output is the area, right? So in this case, if I try to highlight, right, the blue region, this is the area, right? Now, why cannot I extend the height of this blue region? What is not allowing me to uh, extend the height of the blue region, right? The minimum height. Okay. the third bar. Absolutely correct, right? So someone says we need to find. Ramesh says we need to find the two extreme bars with maximum heights. Okay, let's see what Ramesh is saying, but I don't think that's correct. So suppose you have two very big bars, okay, and maybe you have some small bars as well, right? Now Ramesh says, let us find the two big bars. One bar is this, one bar is this. Can I say I will take this as the base of the rectangle? Maybe, maybe not. But what's going to happen? Who is going to restrict the height of the rectangle? Who is going to restrict the height of the rectangle? This smaller bar, right? So if you take this smaller bar as a part, you cannot make a rectangle that is going outside the height of this rectangle, right? So that means you are only restricted to this part. Does it form the largest rectangle always? Possibly not. Okay, possibly not. A better rectangle might be that if you take this much part itself, it might give you a bigger area, right? It might lead to a bigger area, right? So of course, so finding the two extreme bars will not necessarily lead to the right solution, right? Okay, let us just discuss maybe brute force logic, right? For that, I will again need the previous diagram, right? Okay, let us just talk about the brute force logic. Let us assume that my starting point, the first bar I'm going to take, right? So I say, okay, let me take this bar, right? Where I want to end, I don't know. So what could be an ending point? Can I say the ending point could be the same bar, bar one? How much area I can get? What is the height and width I can get? Tell me. 2 into 1. Absolutely correct. Right. So in this case, if I just take the first bar, right, I know the height is going to be 2, the width is going to be 1, the area is 2. Very good. Basically this part, right? But I say, okay, I will start from 1 only, but I will end at 2. If I take these two, what should I know? What should be my width? The width, I know width is very simple to calculate. These two indices, right? So 2 minus 1 plus 1. So width is going to be 2. But how do I compute the height? Out of these two, I take the one which is minimum. Absolutely correct. So the minimum is this height, um, which is 2, right? So the area is going to be 4. Tell me, does that make sense? We are calculating this, right? Okay, now I say I'll still have the same starting point, but my ending point is 3. Okay, what should I do? I still need to track out of all these three what is the minimum, right? So the minimum is still 2. So width is 3, the height is 2, the area is 6. Okay, what about 4? Let's include this. Start is 1, end is 4, the height is 2. The minimum in this range is 2. So the width is 4 now. The area is going to be 8. Okay, let's do this as well. Fifth one. Start is 1, end is 5, height is 2, which is minimum, right? And width is 5, the area is 10. Okay. What about if I include end as 6? This height is 1. What will happen? Width I know is 6, but what is the height now? What height we will get? 1. Absolutely correct. So height is nothing but the minimum, right? The minimum across this. this height, right? No, you still get a rectangle, right? You still get a rectangle, but now the height is decided by this part. Ankur, the rectangle still can be formed, but the height is now restricted by the minimum bar, which is of length 1, right? So I'll say the height is actually 1. So the area is going to be 6, right? Very good. So we got to know that if I include the first bar, the maximum area I can get is actually 10, right? Now, can I say I can do the same thing for second bar? If I start with second bar, end as second bar, end as third bar, end as fourth bar, and so on, right? So how much time we will end up taking, right? So what is we are doing? We are saying that for start as every bar, you start with every bar, right? You take end as uh, every bar greater than equal to start, right? Okay. Then you say, okay, my width is how much? My width is how much? Who will tell me? If I know the start and end, how much width I will get? E minus S. Okay, so if end is 2, start is 1, the width is not E minus S, it is E minus S plus 1. Okay, but if they are array indices, right? Suppose if it is a zero based indexing, right, which will be the case, right? So the indexes might look like 0, 1, 2, right? So 1 minus 0 plus 1. Again, yes, we have to do plus 1 in every case. So the indexing does not matter. That will be the width, right? What will be the height? How do I get the height? Minimum, right? So the minimum of the array from array of start till array of E. That is the minimum, right? And my area is nothing but W into H, and my largest is nothing but largest I say is 0 in the beginning. So largest is the maximum of the largest I have seen so far, and the current area, right? And finally you can say I'll print the largest. So tell me, did you understand this algorithm? If yes, then what is the time complexity of this algorithm? People are saying n square. See, you are not taking into point how this value is going to compute, how we are going to compute the minimum. Now there are two ways. The minimum, if you put a loop here, it will take order of n time. Is there any other way to compute the minimum? Is there any other way to compute the minimum? Carry forward, absolutely correct, right? You can also use the carry forward technique. You can actually compute minimum in order one time. You may ask how. Let's see. Let's see. So suppose you know the array from start to E minus 1. Let's say the minimum is, let's say, 6. Okay. Maybe the elements are 12, 6, 8. So you know the minimum is 6. And suppose you got a new element at this position, which is 4. So how you can say the new minimum? What you can say about the new minimum? The new minimum. What can be done? Can I say minimum of S to E is nothing but its minimum of the current element, which is array of E, comma, the previous minimum which you have already known to you. Can I use this recurrence? Can I say, okay, see what is the minimum till now, and whatever is the next element that we are getting, if the next element is smaller than the previous minimum, then update the minimum, otherwise carry forward the same minimum, right? So here we are getting a 4. So what's going to happen? The 4 will be the new minimum. But if the element would have been 14, you would have said 6 is the minimum, right? Tell me, does this make sense? The minimum can be computed using carry forward. Order 1 at each position, okay? Order 1 at each position. Tell me, does this make sense to you? Or should I dry run? Okay. Ankur says dry run. Okay. People are saying me to dry run. Okay, fine. I will be happy to do the dry run also. Right. So right now, if I simply do it using the loop, the complexity of this algorithm will be order of n cube. Because the finding of minimum is also going to take linear time. You're going to iterate from start to end. Fine. Right. Let's say how we can make it as order of n square. Right. Fine. Now suppose I say I'll start from 1. Fine. I will end at 1. Okay. What is the minimum? The minimum height is 2. Fine. Right. The minimum height is 2. Okay. I don't have anything here. Right. And my width is going to be 1. 1 minus 1 plus 1 width. So my area is also 1. Very good. Start is 1. End is now at 2. Right. What is the current element? So minimum will be minimum of 2 comma 4. What is the minimum? 2. See what I'm doing? I'm saying minimum, किसका minimum लेना है? 2, 4 का minimum लेना है, right? So answer is, so width is 2 and the minimum is 2. So the area is 4. Fine. I say my end is going to be 3. I go to this element. What is the height? It is 3. So minimum is 3 comma 2 ka minimum, which is still 2. Okay, so 2 into 3, which is 6. End is 4. Okay, so I go to this element. The current height, array of I, this is 4. So I take minimum of 4 and the previous minimum. What is the minimum of this range? 2. So the minimum is still 2. Oh, sorry, height is 4, width is 4, minimum is 2. So this data is 8. Tell me, does this make sense? What you know is you already know minimum of S2E minus 1. And while computing minimum of S2E, basically at the current index, you are saying take the minimum of the current element and the previous minimum, which is the minimum of S2E minus 1. Right? Tell me, does this make sense? Right. Got it? So doing this way, you can find the minimum in O1 time. Right? And if you do this change in the code, right, you will get the overall complexity to be order of n square. Right? Order of n square using carry forward technique to find the minima. Now tell me, does anyone still have a doubt? Okay, feel free to ask. If you have doubts, please let me know. I have a doubt. We will just maintain minimum in a minimum array. You don't even need an array. What you need is a variable. Chandra? Swati says question. So Swati, the question is like this. We are given a bar graph like this, and we want to create a largest rectangle which does not go outside the boundary of the bar graph. Okay, that's what we are doing. So let's do one more attempt, right? But this is still not the best solution. The best solution is yet to come, right? Let's draw the bar graph again. So we have bars 1, 2, 3, 4, 5, 6. The bars have a height. So 1, 2, 3, 4, 5, 6, let's say. Right? So the array looks like 2, 4, 3, 4, 5, and 1. This is the input array given to us. So then I have a bar of height 4, which means it's like this. Bar of height 3, okay. Bar of height 4, okay. Bar of height 5, okay. Bar of height 6, of height. Right? I want to create the largest rectangle. Right? Now let us look at other way. Right? Let us say that I want the ith bar to be part of my answer. Okay. Suppose I want this bar to be part of my answer. This is the third bar, right? So I want to say, okay, let us assume that if uh, third bar is included, right, is included in the answer, then what is the largest area I can form? Who will tell me? If I say, okay, I definitely want to take this bar, what is the largest area of the rectangle I can form? Okay, people are saying 12, right? Swati, Saraswati says 12. Ankur says 4 into 3, right? Well, that's correct. So how you're thinking? Can I say you are trying to expand in the right direction by saying, okay, this can be included, this also can be included, but this bar cannot be included. And you're also going to expand in the left direction. You can say, okay, this can be included, but the this bar cannot be included, right? So basically, what's happening? The bars which are smaller, the first bar which is to the left of this bar and it is having a smaller height, that cannot be included, but everything after that can be included, right? So can I say the area is going to include this part, include this part, right? Right. So if I include the third bar, right, what I'm looking at, I will go left, right, to find a bar. Maybe this has an index called, let's say, P1 or B1. Okay, let's say this has a index called P1. This has an index called P2. So what are these P1, P2? P1 is the index of bar on the left, which is less than the current bar, the ith bar. P2 is the index of the bar on the right, which is less than current bar. Tell me, does that make sense? Now, once you know P1 and P2, can I say I know the width? At least I know the width of the rectangle. How much is the width? So it is how much? 4. So can I say it is nothing but P2 minus P1 minus 1 or plus 1? Come on, tell me. Minus 1. Okay. The width is nothing but P2 minus P1 minus 1. Right. So it is nothing but 6 minus 1 minus 1, which is 4. Okay. What about height? What should be the height? Is it the height of the ith bar or is it the height of the minimum bar? Should I take the minimum of a range or should I just take the height of the current bar? current bar. That's correct. That's correct. So it is nothing but its array of I. Why? Because we are moving in a way such that we are ensuring the bars which are included, they have at least this much height as the current bar. Right? So I know the height of the ith bar is nothing but it is 3, and this is 4. So the area is nothing but 3 into 4. Right? So by standing at the current bar, how much time we spent? How much time we spent at the current bar? See, if I take two variables to iterate, right? Now it depends upon how do I calculate P1 and P2, right? So if I iterate at every I, it will take order of n time, going left and going right. Yes or no? Tell me. Going left and right, it will take order of n time. And if I do it for all the bars, it will again take order of n square time, right? But, if we don't do this, if we do what we did earlier, right? If we do the pre-computation, if we pre-compute the array, right? Do it once. I do it once for this array and I do it once for P2. How do we do it? Like we did in the previous class. What we learned in the previous class, that for every element we can find the smaller element to the left for every element using stack. We built this algorithm in the last class. Do you remember? Yes or no? See, we did this, right? For 8, we know the previous, the smaller element is 3 and it is present at this index, right? So we noted the element, we can also note down the index, right? So this is we have already solved for, right? So the P1 P2 part is something we have already solved for, right? So what I need to do is I need to compute the P1 array which stores the minimum index, right? So maybe I'll do it for this array, right? Let us write P1. What is to the left of 2? I don't have anything, so I'll store -1. What is to the left of 4? 2. So the index is 0, right? Smallest index on both sides. That's correct. That's correct, right? Less than, right? Less than the current bar, right? Fine. Okay, for 4, the smallest index, the element is, this bar is 2, the smallest element is 1, so the index is 0. Okay, so I'll store the index instead of element. That is one change that we need to make. But anyways, you can do that change in the algorithm, right? Instead of storing the element, you can store the index. What about 3? Okay, so for 3, the element is this, which is having an index 0. For 4, it is 3, right? So 3 is having an index 2. For 5, the index is this, which is having an index 3. For 1, the leftmost index is, uh, we don't have anything, right? So we say -1. That's correct. Tell me, did you understand this array? This can be pre-computed in order of n time. Tell me, do you understand this array? In the same way, you can calculate P2. In the same way, you can do it, right? Again, it will take order of n time, right? Once you have this P1 and P2 array, right? What do you need to do, right? You simply need to put a loop, right? You also, okay, for every bar bi, right? What I need to do, I need to get the first smaller element on the left, which is P1, right? So we okay, get the left. So it will be given by P1 of I. Uh, I need to get P2. So I need to get right? So, so get the smaller element on the right, which will be given by P2 of I. Right? Very good. Right. Now what do you know? You know the width. Width is P2 minus P1 plus 1. Fine. Right? And height. The height is nothing but B of I. Fine. Area is nothing but W into height. Fine. And the largest is nothing but the maximum of the area and the largest. Tell me, does this make sense? Oh yeah, P2 minus P1 minus 1. That's correct. How much time now you're going to take? Tell me. So now these values are pre-computed. So you just do it in order 1 excess, right? So now this is going to take order of n time. Right? So you will still get the largest area under the histogram in linear time. Right? Tell me, does this make sense? Right? Now there is one small catch here, uh, which is there while computing the P2 array. Right? Suppose I have this element. This is of height 2. This is of height 3. Right? Suppose I have these two elements. Right? Let us try to write P1 and P2. Do I have anything smaller on its left? No. So I say P1 is minus 1. For this, do I have anything smaller on the left? Yes. So the index will be 0. Right? Fine. What about P2? Do I have anything greater on the right? Oh, sorry, smaller on the right? No, right? What does it mean? What does it mean? If I start with 2, can I include this element? Yes or no? Come on. Of course, yes, I can include this element, right? So I want to calculate the width, right? So where should I stop? Can I say if I do not find the smaller element on the right, I should stop at the nth index. I should stop at 2, right? If you stop at 2, what is the width you will get, right? Let us calculate the width for this position. So width is nothing but P2 minus P1 minus 1. So it is 2 minus minus 1 minus 1. So it is 2 plus 1 minus 1. 2. So I'm getting the width as 2. Is this the correct width? And what is the height? The height is 2, right? The height is area of 5, which is 2. So I'm getting the area as 4. So do you see is it the correct width? Of course, yes, it is the correct width, right? When I say I will take everything between P2 and P1, right? Come on, tell me. This index is P2. This index is P1, right? So I'm saying take the distance in between, right? Something like this. Oh, sorry. This is not P1. This one is P1, right? So I'm saying take this region between P2 and P1. Tell me. This is what we are doing. We are saying between 2 and minus 1, which is here, how much area we have, right? I have 2 units. That's what the width I get, right? So what I'm claiming is that if you don't, so when you're finding a smaller element to the left, and if you don't get such an element, put a minus 1, right? But if you're finding a smaller element on the right, what you should put here? Should you put minus 1 or should you put 7? We should put 7, right? That's what I'm trying to tell you is that if you don't find an element on the right, so suppose for this element, if I say, okay, find the smaller element on the right, I could not find a smaller element. Suppose I put minus 1. So what is the width I will get? I'll get minus 1, minus minus 1, minus 1. So my answer would have been minus 1. But this is not the correct width, right? So what I need to give is I need to substitute this value with the number of elements in the array, that is n, right? And in this case it is 2. So basically put n if right smaller element does not exist. That means you can take everything before the nth position. Everything up to n minus 1 can be included with the current bar. Does that make sense? The very simple reason is everything up to n minus 1 can be included with the current bar. Tell me, does this make sense to you? Yes or no? Okay. So that is one small change that you will make, that if the right smaller element does not exist, put n here. Right. Now for 5, the next smaller element is there. So it is at index 6. For 4, it is again at 6. For 3, it is also again at 6, 6, 6, something like this. Okay. So this is how the P2 array would look like. Now you can do the run this algorithm and you will get the largest area in order of n time. Is it clear? Shall we proceed to the next problem? Scroll up for 1 minute, okay? Yes, Hardik. Got it. Very good. What if the last bar is 2 instead of 1? If the last bar would have been 2, then again the answer would have changed, right? So we could have included it with this bar, the first bar, and we can still get an area of 12 starting from first bar. P1's last index is 1. P1's last index. Okay, let's complete this, right? So if I come to this bar, the element on the left has an index 0, fine. The element on the right has an index 2. So here also I would say it's uh, 2 minus. See, if I start with this bar, if I say, okay, I want to include this bar, how much area I can get? I'll get the width. So width I'm getting as P2 minus P1. So 2 minus 0 minus 1, which is 1, into height, which is the height of the current bar. It is 3. Right? So 1 into 3. So I'm getting 3. So do you see the algorithm works on 2 bars also? If I say, okay, I will include the 0th bar, I get an area 4. I want to include the first bar, which is of height 3, I get an area 3. Right? Tell me, does this make sense? This is for bar 1 and this is for bar 0. It will work, right? For all bars. Fine. Okay. Next question, right? So we are given a matrix. Where did we use stack here, or is it the homework? Stack is used here, right? To calculate this array. This is the stack algorithm that we discussed in the last class. Yes or no, Ramesh? The way we calculated the P1 and P2 array, right? This is done using the stack algo. So P1, P2 compute using stack algo. So it is order n work here, order n work here, plus the order n work here. So it's overall order n, right? So this you have to do it, right? How come 2 bars we have taken 3 indices? For 6 we have 6, I guess. Shivam, which example, right? This one, right? This one. No, no, it's like this. See, if you have 2 bars, one is of height 2 and another bar is of height 3, right? So I'm saying the indexes, right? So the indexes are 0 and 1, right? And maybe this index is -1, this index is 2, right? Which is okay. We are not having these indices in the array, but we will still say, we can say n is 2, right? The number of bars is 2, so I can say n is 2, right? So what I'm saying is you will compute the P1 array. You will also compute the P2 array, right? So P1 array, look for the smaller element to the left of 2. I don't have anything, put -1. Look for a smaller element to the right of 3. I don't have anything. No, I have this bar which is of height 2. What is the index of this bar? 0. Fine. Now do it for this bar. What is the element which is on the right and it is having less value than 2? I don't have anything. So what should I put here? What should I put here? I should put n, that is 2. So this value is n. Right? Go to 3. What is the element which on the right which is smaller than 3? I don't have anything, so put n, which is 2. Right? Now I am saying that if you start with this bar, so for every bar, if you start with this bar and you say, okay, I'll include this, that means on the left and right, this much area should be at least included. That means this area will become part of it, right? So what I say, width P2 minus P1. So it is 2 minus 1 minus, so 2 minus -1, right? So it becomes 2 plus 1 minus 1, which is 2, into the height of the current bar, which is 2. So how much area I get? I get area 1 as 4. Okay. But when I go to this position, I say, okay, fine. I want to include this bar. That means this much height I need. So what is the left I can include? So the left is nothing but everything after the 0th index, right? So I don't count 0th index. So I say, okay, width is nothing but P2 minus P1 plus 1. So P2 is 2. So 2 minus 0 minus 1, which is 1, into the height of the current bar, that is 3. So I get 3. So area 2 is 3, right? So what is the maximum I get? Is still 4. Does that make sense now, Shivam? This is what we are doing. That's it. That finishes off the question, right? So we are still iterating over 2 times. We are not iterating over the third index. That's it. Right? So this value is only used here to substitute if I don't get anything greater on the smaller on the right. Fine. See, understanding this question is important because the next problem is based upon the current problem. Right? So once again asking, is it clear to everyone? If that is not clear, you will not be able to solve the next question. Siddharth says, please explain again. Okay. I'll try to do it. Just give me a minute. Okay, people are saying me to explain again. All right, fine. So I'll do a quick recap, right? So we have time today. Uh, we'll not rush, okay? Just the question and the recap. Fine, fine, fine. So there is a power issue at my end. You have to wait for 5 minutes, okay? Maybe we can give you a small break, 10 minutes. In the meanwhile, I'll try to get the power, okay? And we'll start at 10:35 or 10:40, right? So we'll do a recap, but let me get on the power first, okay? So I'm stopping for a small break. We'll resume. So welcome back, everyone. So light was gone, and I arranged light, okay, through a jugaad. So jugaad has been done, and we are back. Everyone back. Siddharth, right? Great, great. Okay, so I'll quick Satish's evaluation of P1 array for this example. So Satish, you are giving me the example, or you want me to do on the same example? Okay, same example. Fine. See, this is an important question for today. If you understand this, you will be easily able to understand the next problem. So that's why I'm spending time a little more on this problem, right? So this is the input array, right? Maybe I should draw the bars also. 2, 4, 3, 4, 5, and 1, right? Fine. Right? See, the P1 array is nothing but it stores the index of the element which is to the left of the current element and is smaller, right? So for 2, do we have any element on the left which is smaller? No. So what we do, we put -1, right? For 4, what is the element that is on the left and that is smaller? That is 2. So instead of storing 2, I'm saying let us store the index of 2, which is 0, right? So this you have learned in the last class that we can store the element. If we can store the element, we can also store the index. So for 4, I store 0, fine. For 3, I look for the element that is smaller, that is 2. So I again store a 0. For 4, the element that is uh, smaller and it is on the left, it is nothing but 3. The index of 3 is nothing but 2. For 5, this one, the element which is left and is smaller, it is 4. The element is having an index that is 3. And for 1, I don't have any element on the left, so it means -1. So is it clear? P1 array, Satish? Okay. Now, why this evaluation is important? Let's look at the intuition behind this algorithm, right? The algorithm says that, okay, if you are considering the ith bar, if you definitely want to include the ith bar in your answer, that means the rectangle will have this much height, right? The height cannot be bigger than this bar. The height cannot be smaller than this bar. Why? Because if it has a smaller height, that we will do at some other bar. Okay, so suppose if you have this bar and it has a lesser height, then you would have done this evaluation of rectangle at this bar for a smaller height, right? Okay, so not at the current bar. Okay, so we are not going to evaluate this bar for a smaller height. We are going to evaluate this bar for at least this much height, which is b of I. I'm saying height is fixed b of I. Right? Now, how many bars on the left and right I can include? Right. So maybe I have a bigger bar. Maybe I have a bigger bar. Maybe I have a smaller bar. Maybe I have a bigger bar, and a smaller bar. Maybe a bigger bar. Right. Now, who is going to stop the expansion of the rectangle? Can I expand here? Yes. Can I expand here? Yes. Can I expand here? No. Because this bar is smaller than the ith bar. Same goes here. Can I expand here? Yes. Can I expand here? Yes. Can I expand here? No. So what I'm storing is P1 gives me this bar, P2 gives me this bar for any ith bar. Right? And how many bars I have in between, number of bars in between, that is nothing but P2 minus P1 minus 1. That gives me the width of the rectangle, right? And how do I get the height? The height of the current bar, which is B of I. So I calculate the largest rectangle I can form at every bar, and I take maximum of all the rectangles. Now tell me, does this make sense? Okay, is it clear to everyone? Siddharth says yes. Very good. Rohit, what about you, Rohit? Is it clear? Ramesh says please compute P2 as well. Okay, fine. P2. I need to give indices, right? So P2 means what element, at what index I see something that is smaller than 1. At what index I see something smaller than 1. I don't have any such index. So I will simply put 6 because I want to take a difference, right? So I'll put a 6 here. Right? Okay, at what index do I see something less than 5? So that index is 5. At what index I see something less than 4? I That index is again uh, 5, 5, 5. Oh, not exactly 5. It should not be 5. Let's see. 4 is a chota element. It is present at the fifth index. Fine. So that is mhm, that is 5. Less than 3. It is yes, it's 5. Less than 4. It is again 5. Less than 2. It's 5. Yes, that's correct. So 5 is the answer, right? Now how do I get the width, right? Width कितनी होगी? 5 minus 1, 4 minus 1, 3. No, sorry. 5 minus minus 1. The width, right? The nearest is at 2. Which one, Shivam? The nearest element to 2, which is less than 2. It is the element 1, right? Oh, okay. For 4, the smallest should be 3. That's correct. That is correct, right? For 4, the nearest smaller is at 3. That's correct. So, which is at index 2. Good, good, good. Thanks for pointing it out. So, this will be 2, the second index. That's correct. Well, that's correct, right? How much is the width? If you start with 1, how much? Uh, so P1 is in the left and P2 is in the right. That's correct. So P1 is in the left, P2 is in the right. That's correct. So how much is the width? P2 minus P1 minus 1. 5 minus minus 1, 6 minus 1, 5. 2 minus 0 minus 1, 1. 5 minus 0 minus 1, 4. 5 minus 2, 3 minus 1, 2. 5 minus 3, 2 minus 1, 1. 6 minus minus 1, 7 minus 1, 6. Okay. How much is the height? The array itself. 2, 4, 3, 4, 5, 1. Okay, fine. How much is the area? 10 units, 4 units, 12 units, 8 units, 5 units, 6 units. What is the largest? 12. Okay, so area is nothing but height into width. How W of 0 is 5? So Ankur, tell me what is the element to the left of 2 which is having a value less than 2. That element is 1. What is the index of 1? That is 5. This value is 5. Yes or no? So this part I told you we do it in ON using Stark algorithm that we discussed in the last class, right? Okay. Okay, how do we interpret this area? What does this 8 mean? Since we have zeroth index, do we still need to do minus 1 again? See, it is important because you are finding to the left of 0. You are finding out the boundary, right? So this boundary is minus 1, the last boundary is n. So how much in between you have, right? The boundary indices, right? So it's important. Vikram, understood, right? Good. Okay, how do we interpret this 8? What does this 8 really mean? So 8 really means that if you want to include uh, this fourth index, which has a height of 5, the maximum area that you will be able to form is nothing but this rectangle. That is 4 into 2, and that is this area 8. If you include this bar, oh sorry, it's not like this. If you include this bar, right? So it is the third last element, so the third last bar. If you want to go till this bar, it has a height of 4, right? So the maximum that you can go is you cannot go on the left. See, the left index is P1, so the left index is 2. That means you have to stop after 2. That means only till this point, only this bar. The right value is nothing but uh, sorry, this is the left value, this is the right value. So the right value is 5. That means you can go before 5 with this height, which is this bar. So now this area is nothing but 2 and the height is 4. That's why you get an answer 8. Tell me, does this make sense? This area, pink and the green, right? So this is how you interpret all the areas, right? That's what we are doing. So with height 4, we can have a maximum area of 8. With height 3, we can have a maximum area of 3 into 4, that is 12, and that is the largest. Okay, got it? Okay, so we took a lot of time, right? But let's now go to the next problem, right? Which is a step more than this problem, right? So I'm given a 2D matrix of zeros and ones. I want to find out the maximum rectangle area which contains all ones. Which contains all ones. Okay, so let me draw the matrix. I have, let's say, 1 1 0 1 0 1 0 1 1. Okay, so this is a 2D array given to me. I want to find out the maximum rectangle which contains all the ones. Who will tell me how big is the rectangle here? Maybe by directly looking, this seems like the rectangle. Any other rectangle which is bigger than this? Tell me. Any other rectangle do you see it's bigger than this? No, we don't see this, right? Okay, fine. How do we solve this problem? Any ideas? What could be a brute force solution? Look for all rectangles x1, y1, x2, y2. Yes or no? Look, generate all possible rectangles, all possible subarrays, right? And then check whether they contain ones or not, right? So generate a subarray and iterate on this to check that okay, if this rectangle is of size 8, then does it contain 8 ones or not? Right. So how much? So given this rectangle, how much time you will need to check if it contains all ones or not? If I simply give you a rectangle, right? I'm saying just the checking part. चेक करने में कितना टाइम लगेगा? N square, right? Checking is n square, right? So I'm saying that generate all rectangles. So each rectangle has a unique x1, y1, x2, y2. So generating all rectangles would mean you will take order of n4 time. Yes or no? You will need four nested loops. And checking will need two nested loops. So checking itself will take order of n square time, right? So that means in total how much time it will take? N4, n square, n6. N6, right? It will take order of n power 6 time with 6 nested loops. 4 loops for generating and 2 loops for checking, right? That is the brute force algorithm, right? How many days? It will depend upon how big the n is. Okay, so if n is 10 per 6, it might run for years. Okay, lot of time, right? So of course not a good algorithm, right? Let's try to do something else, right? Now this part is little, I would say, difficult to think of, right? But I'll try to give you some hints, right? Let's say I treat this row as a base of the rectangle. Let's say I'll I'm saying that my rectangle will finish in this row. Let's say, like any ith row, I'll treat that as a base, right? So brute force is okay. That will take order of n6 time. But let's try to do something better. Right? Now tell me, what is the largest height I can take with this element? Three, right? I can take the largest as three. Good. What is the largest height of the bar I can take at this row, this element? One, right? Here, zero, fine. Here, zero, okay. Here, one. Here, I can form two. Can I say if I know this? If I know, okay, it's three followed by one followed by zero, zero, one, and followed by two. And I'm looking for a rectangle. Now, because all these elements are ones, I can simply apply my histogram logic here. Tell me, can I apply the histogram logic we have learned here to get at least the largest rectangle which ends up at this row, in this row? Yes, we will apply histogram at each row. That's correct. But tell me, if I apply histogram at this logic, what is the largest rectangle I'll get from the last row? Largest area, right? 3. Absolutely correct. So I'll get that fine. If I do the histogram thing here, I'll get maybe this, which is 3, right? So I'll get, okay, this is 3, right? Okay, let's do it at this row. So the bar height is 2, it is 0, then it is 3, right? Then it is 0, 0, 1. How much we are going to get? Basically this histogram. If I give you largest rectangle you can form in this histogram. Oh, again 3. Fine. So again it is 3. Fine. What about this row? 1. I have 3, right? I have 2. Here 3. Here 2. Here 0. Right? Largest area under histogram for this row. Right? So I'll just highlight what is this row going to contain. So this is the histogram looks like 1, 3, 2, 3, 2, 0. Right. So what is the largest rectangle that we can get in this? So of course, uh, the largest rectangle here is 8. This white dotted rectangle. So do you see the histogram problem is helping us here to find out the largest rectangle, right? So this is going to be 8. So similarly, you do it for the rectangle ending at this row, which is 0, 2, uh, 0, sorry, 1, 2, 1, 2. Here it might be maybe 2, right? Either this way or this way, fine. Oh, it can be 3 also. It can be 4 also. That's correct. This one, it is actually 4. 4 or 5? Oh, it's 5, right? This one, it's like this. It's 5 because I can at least take out 1 unit of height from all these bars. 1 unit, 1 unit, 1 unit, 1 unit, 1 unit. So it is actually 5, and this is clearly visible here also. Fine. If I talk about this row, uh, I get 1, 1, 0, 1, 0, 1. In this case, it's going to be 2. That's correct. So what is my largest histogram then? Out of all these rows, answer I get the max, which is 8. Right? Very good. Easy. Now you see this is going to be a lot better, right? But the question is, how do we compute this matrix? How do we compute these values, right? So look at this matrix and look at this matrix. Do you see any relation between the columns? I have a 1 here, I have a 1 here, okay? I have a 0 here, I have a 0 here. I have a 1 here, I have a 1 here. I have 1 here, I have 2 here. I have 1 here, I have 3 here. Look at top to bottom. Can you figure out something? See, we know that at this 1, we were adding up all the 3 values vertically. Right? Can I build it in this manner? Top to bottom, can I build this array? Something like prefix sum? Of course, yes, right? So what I'm getting is this is nothing but it is prefix sum, column wise, except if you get a 0, that breaks the continuity. Okay, if you get a 0 in the column, if you get a 0, you need to reset the sum to 0. So look at this one. So you get a 1. You get a 0, reset the sum to 0. At this one, the sum is again 0 plus 1. At this one, it is previous 1 plus 1, that is 2. At this one, the sum is previous 2 plus 1, that is 3. Fine. So reset the sum to 0 when you get a 0. Let's look at this column. We have a 1, we have a 1. Another 1, so 1 plus 1, that is 2. Another 1, 2 plus 1, that is 3. We got a 0, reset to 0. We got a 1, 0 plus 1, that is 1, right? That's it. That's it. Now what you can do? So from here to here, how much time you will take to build this prefix matrix? Prefix matrix. Step 1, build the prefix matrix order of n square. Fine. Now for every row, compute histogram. For every row of uh, PM, prefix matrix, compute histogram. How much time for histogram? Linear time. Order n, right? And how much time for every row? You have n rows. For every row, you are taking n time. Order of n square time, right? That's it. And take the max, right? So track the maximum as well, right? Track the max for every row. So we can solve this problem in how much? Order of n square time. Tell me, does this make sense? Any doubts in this problem? Okay, I'll not do the code. Now you can do it, right? It's very much similar, right? This is one famous problem on histogram, right? Uh, there are not a lot of problems like these, right? So it's okay to know these, right? Yeah, it might be asked in an interview. Okay. See, the good thing about the way we are dealing with these problems is we are not giving you the predefined solutions to these. What we are doing is we are doing a bottom-up approach, right? So we learned some technique. We are then building on the top of it, on the top of it, on the top of it. So if you look carefully, we started with this problem, finding the smallest element to the left. Then we applied that to the histogram problem. Then we applied the histogram problem to this problem, right? What generally happens is if you look at a YouTube video, they will directly teach you the solution without giving you the intuition that how you should reach this solution. Okay, so it's a good thing that we are doing in a bottom up manner, right? Okay, all right, so let's do the final question for today, right? And what happens in interviews is that many people would look at a solution at Geeks for Geeks. They will try to memorize this, and in the interview either they will forget that okay, this was the code, or they will try to reproduce the same code without diving into the intuition that why and how this solution came, right? So that's why we are spending 1 hour on each problem so that you get the exact path, because in an interview you will not remember the exact solution. You have to start up in a bottom up manner, iteratively improving, and simultaneously discussing the brute force and other approaches as well, right? Okay, so we are taking time, but yeah, it's worth it, right? So Rohit says it was too much for today. No, it's not too much. Let's do one small problem, not I would say very hard problem, right? So given n array elements, right, find sum of max of every subarray. Aha, maximum of every subarray. Okay, let's take a very small example, I would say, right? Because there are too many subarrays to handle. So what is the subarray we can get? Subarray can have single element 1, it can have 4, it can have 3, it can have two elements 1 comma 4 or 4 comma 3. Can I have 1 comma 3 in a subarray? No, it's not a subarray, it's a subsequence. Okay, what else? I can have the complete array as a subarray. What is the maximum for each of the subarrays? 1, 4, 3, 4, 4, 4. So 4 is coming 4 times. So 4 contributes 16 plus 3 plus 1. The answer here is 20. Okay. So this is the sum that I need to find out. Tell me, does the problem make sense? If it makes sense, then who will tell me the brute force? Can we have negative also? Yes, negative numbers can be there. Right. Tell me, brute force, two for loops. Saraswati says contribution technique. Fine, good. Two loops, three loops. Finding the subarray itself is how much? Two loops. Now getting the maximum. How do you get the maximum in this range? If you do it using another loop, you will end up taking order of n time, right? And that means this is going to be a order of n cube solution. Prefix sum, that's correct. Two loops with carry forward, that's correct. So maximum can be done in, or you can use carry forward. At ith index, you say, okay, this is the maximum. But when you go here, you say this element is bigger. This is the maximum. So it can be done in order of n square if you use carry forward. That's correct. Right? Fine. Anything better we can do. Anything linear we can do. So Saraswati has given us a very good thing. If you remember, we solved a similar problem in 2D arrays where we had to find out sum of max of every 2D array, something like that. Every subarray. Do you remember something like this we have done in 2D arrays? No, not exactly mango trees, but uh, where we were checking that how much each. I think the question was sum of every submatrix, something like this, where we said we can have n4 submatrices and summing them all might take up n6 times. Brute force. Given a 2D array, find sum of all submatrices, something like this. You might have remembered. Okay. So, anyways, uh, maybe you remember or not, but one technique we discussed was we will count how many times each element is getted added in the sum. Can I say that if I get to know the contribution of 4 in final sum, that will make my life easier. If I know that 4 is going to contribute 4 times, I can just do it in O1 for 4. If I get to know 3 is going to contribute these many times, my life would be easier, right? Good. How do I get to know? Now, the thing is very simple. Any subarray that starts either at 4 or before 4 will include 4. Yes or no? Any subarray whose starting point or starting index is less than equal to fourth index. Let's say this index is some whatever. It will include 4. But is that true? Will 4 be okay? Let me put it like this. Let's say 6, 5, 1, 2, 4, 3, right? And maybe 2, 7. Okay. So if I talk about this array, right, and I'm talking about this index 4, in what subarrays 4 will be the maximum element? Let me put it like this. No, no, this time it was internet. Okay, the current is still there. Okay, okay. Is the screen visible? Fine. So what I was saying, that any subarray that includes 4, right? So if I say the subarray starts with 6, will it ever include 4 as a maximum element? If a subarray includes 6, can 4 be the maximum? No, it can never be, right? So what I'm looking for, all possible places, like if all subarrays that start with 1 and include 4, right? Anything that is starting from 1 and ends either at 4 or after 4. Yes or no? For example, 1 to 4, because all these elements they are less than 4, right? Okay, and maybe up to this point I can take. They are also less than 4. So effectively, I'm getting a window from here till here, right? How many subarrays I can form in this window, which include 4? That means if I want to build a subarray, the starting point of the subarray can lie in this range. The ending point of the subarray should lie in this range. Tell me, does this make sense? For example, if start is 1, so I end up at 4, or I end up at 3, or I end up at 2. All these subarrays will give me 4, right? What about if I start with 2? Fine. 2 comma 4 can be a subarray, 2 4 3 can be a subarray, 2 4 3 2 could be a subarray. Fine. All these arrays still have 4. Right? I can also start from 4. I can have 4 as a subarray, 4 3 2, 4 3 as a subarray, 4 3 2 as a subarray, right? So effectively, I'm getting there are three arrays here, three arrays here, and three arrays here. So I get 3 into 3, that is 9 subarrays will include 4. Okay. So how do I decide this? Can I say it is nothing but the number of ways I can pick the starting point into the number of ways in which I can pick the ending point? What I need? I need a start and end such that 4 is included. So in order to pick start, I can have this as a start. So I have 3 ways. In order to pick an end, I can pick this 3 ways, 9. Right. So how much will be the contribution of 4? So into 4. That will be the contribution. 9 4s are 36. So 4 will contribute 36 in the final answer. If I do it for 4, can I do it for every element in the array? Yes or no? Right. Yes or no? Right? Why not? Of course, yes. But how do I do this? How do I find the start and end range? Range start. What I need to know for 4? Can I say I need to know the element which is bigger than 4 and to the left of 4? Previous greater and the next greater. Absolutely correct. For 4, what I need to know, two values. One is p1, the index of the element which is on the left and it is greater than 4, right? And an index p2 which is of the element that is to the right of 4, right? And here comes the stack. That's correct. So Ankur, now you are uh, on track, right? Very good. So what I need to do for every element, so I'll say compute p1 array, compute p2 array. So basically for every element, find the left greater element and the right greater element. This this can be done using stack. Just pre-compute it in order of n time, right? And you store the indices. You store the indices in this array, right? So let me maybe do it for one example. Not fully, but maybe little bit. 6 5 1 2 4 3 2. 1 2 4 3 2. Right. Okay. Now tell me what is the index for, let's say, 2. Uh, let's do it for 4 only. And 7. Okay. So I have 0 1 2 3 4 5 6 7. Index of p1 1. Index of p2. That means I can start the start after p1, right? So p1 till the ith index. How many elements I have? In how many ways I can choose the starting point? Tell me. Starting point of the sub array. 3 तो ठीक है, but in terms of I and p1, I minus p1. Okay, so I can choose the start for I is I minus p1, which is 4 minus 1 3. That's correct. I can choose the start of I in I minus p1 ways. What is end of I? In how many ways I can choose the end of the subarray so that 4 is the largest element? Everything from the ith index before p2 index. So 7 minus 4. That's correct. So it is nothing but p2 minus I. That's correct. So what I will include in my answer? Start I into end I into what? Contribution, right? So the array of I. Do it for all I. Khatam. How much time you will take? How much time it will take? linear time, right? And that is the beauty of Stark. So computing these values, they will come using you have to pre-compute using the Stark based algorithm, right? Compute it. Okay, so P1 of I, P2 of I. That's it. Okay, so can you do it now? Not very difficult. Easy, right? It's a simple counting problem. If you know how to compute the previous greater and the next greater element, that's it. Okay. So if you don't have any doubts, I'm okay to end here. But if you have any doubts, I'm here to stay. Okay. Google form I did not share. I'll do it in the next class. Okay. Thanks for the reminder. I forgot about it. Will do. Will do it. Okay. All right. Thanks everyone. If there are no doubts, we can call off for today. Bye bye. Good night and take care. Okay. Uh, Fine. Okay. Good night.